Okay, so let's go ahead and calculate some delta H's using what we call the heats of formation. So, um, the last video or the other video that I had was using Hess's law to calculate delta H's for chemical reaction. And sometimes we have chemical equations that will allow us to do that, to manipulate them back and forth. So we can go ahead and calculate the delta H for our reaction. But sometimes we don't have that. But we do have other informations that, well, other times we need to use Hess's law, but sometimes we have what we call heats of formation. And heats of formation are basically just the delta H of the process of making compounds from their elements. And so on page 921 of your textbook, which is part of the appendices, so if you're looking for this table, it's in the appendix, or as I put out appendices on School Loop. On page 921, it's Appendix C, and there's table C31, and it looks like this. So this is heat of formation values for a select amount of compounds. So if you look these up, there's really like 4 columns worth of substances here. And each of the columns has columns within themselves, right? So there's the substance here and the heat of formation next to it. You can use these heats of formation to calculate the delta H of your chemical reaction by just using a simple equation. Basically, just look up the heats of formation of the products, multiply H1 by the coefficient of the reaction in the balanced chemical equation, and then subtract it from the heat of formation of the products, also multiplied by their coefficient. There was an equation I put up on the PowerPoint. I don't have it available right now, but basically that's all it's saying. So let's do this. Let's try to figure out delta H for a couple of chemical reactions. So there's chemical reaction 1, NO plus O2 goes to form 2NO2. And the second one is CaCO3, breaks down to CaO plus CO2. We're going to use the heats of formation. And heats of formation, make sure that I have this thing working. Heats of formation are represented by delta H subscript F. So that's what represents a heat of formation. So with all these are delta H subscript F. So let's go ahead and actually do the problems here. And I think it's pretty simple to do. So the first chemical equation that we have here has NO2 as the product and NO and O2 as the reactants. So what we're going to do is we're going to look up a few things. Now, let me just go ahead and write this out. Equation. As an equation, I can write this out. This is what we're doing. Again, the delta H of the reaction. So this is the delta H for the whole reaction. It's going to be equal to, since the coefficient is 2 for this, it's going to be 2 times the heat of formation of NO2 and since that's the only product, then we're going to then subtract the reactants. And the coefficient for the first reactant, NO, is a 2, so it's going to be minus, and you know what, I'm going to put this as 2 times the heat of formation of NO plus the heat of formation of O2. Now, the coefficient for O2 is just 1, so it's just going to be the heat of formation of O2. And these are things we can look up in our table here. So if we can look up here the heat of formation, let me change the color here. Heat of formation of NO, which is one number. The heat of formation of, sorry, that was NO2. Heat of formation of NO, which is another number. And heat of formation of O2, which is a third number. Actually, the heat of formation of O2 is actually 0 because O2 is an element and it's in its elemental state. So any element that you see in its elemental state is going to be a 0. And we'll see right now when we look at the table what it is. So take a look at look these things up. 2 times the heat of formation of NO2. So we're going to go ahead and click over here and look for NO2. NO2 is right here. Third column, almost near the bottom, and its heat of formation is 33.18. 3.18. So we're going to use that over here. 2 times 33.18 minus. Now we need the heat of formation of NO. And if you'll notice, these here are pretty much alphabetically arranged. So NO is right next to NO2 in the third column near the bottom. The heat of formation of NO is 90.25. So we'll use that times 90.25 plus the heat of formation of oxygen. And as I told you, oxygen's heat of formation is 0, but you can go and confirm it. So if you go to the fourth column over here, O2's heat of formation, there is 0. So we're going to put a 0 in for that one. And there's your calculation. You should be able to calculate your delta H for that reaction. It's going to be 2 times 33.18 minus 2 times 90.25 plus 0. So let's calculate that out. 2 times 33.18 minus 2 times 90.25. Don't forget your using your algebraic logic. In other words, you have to take that 2 and times 2 times 90.25 before you subtract it. Otherwise, if you try to subtract 2 and then multiply by 90.25, it'll give you the wrong answer. So the correct answer I get is minus 114.14. Negative. It's an exothermic reaction. I'm just going to put as minus 114. Oh, actually, 114.14. Yeah, both of these had 2 decimal places. So I can go ahead and put that in there. And these are in kilojoules per mole. Sometimes I just put kilojoules, but if it's delta H for a reaction, for a chemical equation, then you can mix it kilojoules per mole. So that's 114. I don't know about my writing. I was hoping that my writing would improve on this tablet. It seems to sometimes go up and down. Negative 114.14 kilojoules per mole. And if you go back, all we did was looked up the heat of formation of NO2, multiplied it by 2, minus looked up the heat of formation of NO, multiplied that by 2, and then the heat of formation of oxygen, which is 0, and did the calculation, and there you go. So that's the first problem. Second problem is just the same way. So let me go ahead and put a line here, separate the 2 out. The second problem, we're looking at delta H is the heat of formation of calcium oxide. There's no coefficients. That makes it a little easier. The first, remember this products first. So calcium oxide, the first product, plus the heat of formation of carbon dioxide, CO2. And then those are the 2 reactants. And then you subtract the products. Oh, sorry. Those are the 2 products. We do the products first. And then you subtract the reactants. In this case, there's only 1 reactant, so we're looking at the heat of formation of the 1 reactant, and that's CaCO3, calcium carbonate. Let's go ahead and do that. CaO, what is it? Let's go ahead and go to the appendix again. Once again, page 921 in your book, which is found in the appendices, appendixes. Calcium carbonate, where can we find it? Right here. I was worried that it wasn't going to be here. Calcium carbonate is negative 1206.9. Oh, wait. First thing we're looking at is calcium oxide. Negative 635.1. Next, negative 635.1. So calcium oxide, negative 635.1 plus now heat of formation of carbon dioxide. Carbon dioxide is, where's carbon dioxide? Above it a little bit, all these in the first column. Negative 393 point, I'm just going to put negative 393.5. Negative 393.5. Okay, we're going to add the negative. In other words, we're going to subtract. Minus the heat of formation of calcium carbonate. And we looked that up earlier. Carbonate is negative 1206.9 minus a negative 1206.9. Okay, so there's our equation with the numbers substituted in there. Heat of formation of calcium oxide, that's changed to blue. This is the equation that we're doing. So calcium oxide is this one. That's its heat of formation. Then plus the negative 393.5, that's the carbon dioxide. So we've got the two products first, and then we subtract the reactant, calcium carbonate. You know what? Just people notice that calcium carbonate is our reactant. And so these numbers are the products. And this number here is the reactant. And so now when we go ahead and put all these together in the calculator, in other words, add them up, what we're going to get, or subtract them, however you want to look at it. Negative, oops, that was a minus. Negative 635.1 plus a negative 393.5 minus a negative 1206.9. My calculator tells me that we get an answer of positive 178.3. Reaction is endothermic. It is positive, or just put positive, 178.3. This is our answer, kilojoules per mole. Okay. So there's your delta H for this reaction. We did two of them, two sample problems here, because this was pretty easy. All we had to look them up in ROR, we just looked them up here on table C13 in your book, page 921 in the appendices. You can look them up there. Okay, so that's how you use heats of formation to calculate the delta H. Just like Hess's law, you're trying to figure out the delta H of a reaction whose delta H you don't have. This one, all you have to do is look at the heats of formation. You can't always use this because you don't always have the heats of formation, but when you do, it's a pretty easy one to do. Okay, hope that helped.